So, hello everyone. Today I'm gonna present part of my work thesis that I made in ISTEP, mainly with Loïc Labrousse. And the aim was to bring together the community of the petrologists and geophysicists to provide a more advanced interpretation of geophysical images. And this convergence between communities became possible thanks to a major recent seismic campaign, Alps and Red Sea, as presented by Georgi, and providing a high resolution of 3D models of the alpine basement. And from the 2D profile, from which 2D profiles can be extracted. And for example, along this one, we have both ACE-wave tomography models and receiver function model. And here is a result of the both models. So with P to ACE conversion in this model here. S velocity variation in this model here. And so what we see first is a plotting panel here, whose properties change, at least in the crustal parts, with an increase here in S-wave velocities and a discontinuous conversion, positive conversion here, associated to the European move here. And it's also changed in the front of the bell here with a low VS anomaly here associated to the negative conversion here. And we therefore have evidence of changes in the rock properties. And if we consider an homogeneous lithology along these dependent panels, what happened to these rocks here? The eclositization of the lower crust has been suggested, but this transformation is expected at greater depth and does not explain this lateral change that we can see here. And in fact, it's the only metamorphic transformation from which seismic properties are not, or more or less. So if we want to provide an alternative interpretation of the eclositization, what we need is to assess the effect of metamorphic process on seismic property of the rocks. And to do this, we follow a direct approach. We calculated or measuring seismicity of seismic velocity of the rocks, and we then comparing them with the result from the inverse method. So that's what we did in a first paper, and we look for analogous of the European lower crust at the surface, which in reality does not outcrop. So we sampled several large chemistry groups, and we then converted their petrogenetic grid, so as function of P and T, into seismic velocity variation. And what we found was quite interesting. So here is a result of the two different chemistry that are representative of the velocity variations that we found systematically throughout the sampling set. And what we can see is that the velocity steps outline some metamorphic facies. So here you can recognize the amphibolite facies that are associated to low ACE-wave velocity here, the granulite facies here with average velocity, and the eclogate facies here, which generates high ACE-wave velocities for some lithology. And according to the burial context, the rock will not undergo the same mineralogical transformation, and then will not follow the same velocity profiles as function of depth. And in a subduction context, so the blue line here, the eclositization will generate a velocity increase around 60-70 kilometers, while in a collision context, so the green line, the amphibolite granulite transformation will generate velocity around 30 and 40 kilometer depth. So now, if we compare this increase in velocity with the one that we show in tomography model, so it's represented by the gray outline here, which is this velocity along this segment in the zoom of a tomographic model. And first, the amphibolite granulite facies generates a velocity of the same order than that is shown by the tomography. So at least, 4 kilometers per second, while the eclogitization generates velocity above 4 kilometers per second. And in addition, the amphibolite granulate transformation occurs at slightly shallower depth than what is shown by the tomography, like 10 kilometers, whereas the eclogitization takes place at greater depths. However, in a plunging panel, if we take into account the kinetics of the reaction that we did not in our calculation, it is more easier to bury deeper a transformation front than to make it shallower. And I'm not sure you this, but in fact, we tested whether a 10-kilometer offset was possible and what condition in terms of convergence rate, kinetics, and temperature would require to generate this 10-kilometer offset. And in fact, it's really easy to do. Well, even if we cannot claim that we have a unique solution with this direct approach, we have more arguments in favor of the amphibolite granulate transformation than in favor of the eclogitization. However, let's take a look at the difference between these two scenarios, as this transformation will not occur at the same temperature. So we start with a state known from the rock record at its surface with 600 and 800 isotherm here that are deflected by the subduction. And if the rocks eclogitize, so the current temperature at 40 kilometer depth is less than 600 degrees. So the thermal rebalancing is limited. The alternative scenario will be to say that in the ending of the convergence, the thermal rebalancing induces more horizontal isotherm, and then the temperature for the amphibolite granulite facies are reached. So as a first conclusion, we can say, thanks to this approach, we have an idea of the chemistry effect on the seismic property of the rocks here, but our calculation of our bulk velocity, we don't take into account the anisotropy of the rocks. However, what do we expect in terms of anisotropy if in a reaction that consumes amphibolite and produce pyroxene, and moreover, if if the plunging panels subducts and reacts, the resulting anisotropy, if there is any, should be parallel to the slab boundaries. So, do we observe any anisotropy beneath the Alps? And yes, we do. So this is the same receiver function model as in introduction, but this time we have the dependence of the model on back azimuth. So, which is the angle of the propagation wave when it's arrived to the station, and what we see is that it's changing in the plunging panel here when it comes from the east. The Mo conversion here is locally negative, while when it comes from the north, here is positive. And it's changing also in the front of the belt. The negative conversion here when it arrives to the north is less negative when it's arrived from the east. So in this part, in the plunging panel, this effect could be the effect of the dip of the interface. And we can show this effect with synthetic receiver function model. Here you have a 2D layer model with velocity that increase with the depth. And you can see that the P direct waves will be converted in S waves, and at this interface, the signal that is generated will be always positive. And so this is what it's shown here. as function of back azimuth, so as function of the angle of the wave propagation. And if now we give a dip to this interface, a dip to this interface, the initial amplitude here changed with a maximum amplitude in the dip direction, so down dip, as the conversion is stronger here, and a minimum amplitude in the up dip direction, as the conversion here is weaker. And to make things a little more complex, in fact, the signal is not only recorded in one component, but in two, so the radial and the transverse components, which are kind of vectors that record station movement, the movement at the station, and it's depending on the configuration, but the signal could also, a part of the signal could also be recorded on the transverse component. But still, at the front of the bell here, it's back azimuth dependent, and we're expecting a interface that are more or less horizontal. So they are potentially a part of anisotropy, and hence a number of questions arise under what condition in velocity contrast, geometry, and back azimuth can the effect of the dip be differentiated from the effect of rock anisotropy, and how much the anisotropy be oriented in the layer to be visible in receiver function data. So to better understand this, we carried out parametric studies thanks to synthetic receiver function model as previous one. So we first start at the front of the bell here, where the interface are supposed to be horizontal, and we generate some velocity model here that are close as possible as what is shown by the geophysical image. And the gray layer here represents the lower crust here. So we're expecting a negative conversion at its top and a positive conversion at its bottom, which is the mole. And we test several configurations of anisotropy, but I'm only show you two of them. So here it's the isotropic case, and to this gray layer here we had some anisotropy, and here it's an anisotropy that induced by the presence of shear zone and is dipping 30 degrees to the east. And so we test a planar anisotropy, which is like the shape of a pancakes, and a linear anisotropy like shape of a cigar. And we compared the result from the isotropic case, and what we see is that by hiding anisotropy, we have some signal in the transverse component, but it's only with the radial components that we can differ these two anisotropy. And in the deep direction here, you can see that the conversion of the MO is less. The amplitude is decreased, and it's not the case in the planar or isotropic case. And this diminution of the amplitude could if the velocity contrast is strong enough, it could even be change the sign of the conversion. Then we did the same exercise in a station above the potential transformation front. So this time we have some dipping interface, and I'm only show you two models. So the same kind of anisotropy that for the horizontal case, and we observe that the planar result does not differ from the isotropic result, and if it's only if you have a long deep linear anisotropy that there are some change. In fact, a second signal, a second signal is superimposed on the initial one and is cutting off the maximum amplitude here in the radial, and it half the initially p periodicity in the transverse. So the next step is to look at the real signal as function of back azimuth, station by station all along the belt, and to see if they match or they are closest to one of the patterns that we modeled. But it is not trivial, and it's still work in progress. So I'm only show you the result for a station that above the external crystalline massive here, whose records the low VS anomaly velocity here. And so here there are two components, radial and transverse, and the first conversion highlight here is associated to the low VS crust, and the second is associated to the Mo crust. And this time, so of course the signal is real, so it's obviously incomplete, but it's still on the range of 360 degrees, so we can represent it in stereogeographic projection, like if we're looking down from the station, so with low VS crust inside and Mo as it's shallower, and Mo conversion outside as it since it's deeper. So in the radial and in the transverse, and we did the same with previous synthetic model here to make easier the comparison. And in the radial here, for both Mo and low VS conversion, we can observe changes in the polarity of the conversion. And these features are only represented in the along deep linear anisotropy case, and not in the planar and isotropic models. So even if this signal is certainly more complex, as in the transverse component, we do not yet what does it mean, and it's obviously more complex than this one. This is it's certainly more complex than just one part of anisotropy here. Well, if we zoom out and come back to our initial question, we propose that this change in property here are the transformation from the amphibolite to granulite facies. But the question is, are we observing a frozen front, or is it currently progressing? And here is a probable scenario, but not unique. So we start with a granulite granulitic crust, anti-alpine and metastable, that is buried quickly enough to not react, and to locate it here at greater depth in its PT equilibrium domain. And then as the deformation migrates at the front of the belt, it's the large thrust at the surface roots here, and allowing a distributed deformation and the reaction of the rocks in their PT equilibrium PT domain, which this time is the amphibolite domain facies, and this sorry. Okay, and here you have some restored cross-section from Belassen and collaborator, and they calculate convergence rates during different periods of collisions, and they show that the localization of the deformation in the front of the belt, as we suggest here, is take around 10 million years to set up, and this time is more than the time is needed to thermally rebalancing the system, and after the subduction has stopped, and therefore leading for temperature that are appropriate for the amphibolite granulite transformation. Thanks for your attention.